Good morning, students. Once again, welcome back to the my seminar. Today, we are going to discuss the next unit on dynamic programming problem. So, what it means, the dynamic programming problem. So, it refers a complicated problems can be divided into a small sub problems. So, solving one sub problem that will be lead for getting a solution to the next problem, sub problem. So in that way, we can solve the solution for the entire problem. So shortly speaking, the dynamic program. So there is a small introduction. So there is a example. We'll start with a dynamic programming. One of the standard form is talking about the networking. So let's start with the example on this topic. Units. So dynamic programming determines the optimum solution to a n variable problem by decomposing it into n stages, with each stage constituting a single variable subproblem. So what is the a formal introduction? So that is the to get the optimum solution with involving function involving n variable that can be decomposed into small stages. So each stage is constituting a single variable subproblem. So we'll start with one of the application is the recursive nature of computation in DP, dynamic programming, shortly denoted by DP. So computation in DP are done recursively to obtain the optimum solution based on one subproblem can be used to input as the next subproblem. So in this way, the entire problem is settled. So one of the famous application is obtaining the shortest route of a given network. So let's start with as an example in this topic. So what is the shortest route problem means? There is a network. We try to always get the shortest route so that we can reach almost all the destination. Right? So we can cover the entire nodes, shortly speaking. Right? So that is the major things in this, the shortest route problem. So here example is the network. So in this network, we need to travel from 1 to 7 through various cities. Right? So from 1 to 2 or 1 to 3 or 1 to 4, then maybe 5, then maybe 6, and finally we can reach the destination 7. So for each and everything, they given the distance in miles. So for example, a city 1 to city 2, it has 7 miles. Again, 1 to 3, it is 8 miles. It may be miles or kilometer, some distance parameter. So likewise, it is given the miles for the entire network. Now the thing is what? I want to reach to 7, starting from 1, going on any node, but I want the shortest route. So try to find the distance, shortest distance. So how we are going to took this case? So the dynamic programming problem, what it says, we can put it into break it into small sub problems. That is, here we talk it as a stages, various stages. So here we connect like this, the various stages formats. So I am taking from 1, that is, if you consider the 2, 3, 4, so you can reach from 1 only, right? So that is I consider as a stage 1. Again, to reach the 5 and 6, there are 3 possible. That is, either you can move from 2, or maybe you can move from 3, or it may be, if you go for 6, you can move from 3 or 4. So this one I break it into stage 2. Similarly, if you want to finally move for 7, then there are 2 options. One is from 5, or other one is from 6. Right? So I can break this one into 3 stages. Now for each and every stages, we find the shortest distance as well as the shortest route. So here, talking about the stage 1, so it includes the nodes, namely 1, 2, 3 and 4. So I have to start from node 1 to reach node 2. So naturally, so it is only the distance, there is no any other things. So therefore, from to reach 2 from 1, there is only one route is there, that is 7. Similarly, for reach 3 from 1, it is only 8. So that is, it denotes only the distance, only one distance. So that is the things here I put it. Now the thing is what, I have to move from stage 1 to stage 2. So from stage 2, if you want to move from stage 1 to stage 2, then what are other things I have to consider? I have to consider the node 5 and 6, right? 5 and 6. So how do you reach this 5 and 6? Either by 2 or 3. To reach 6, either by 3 or 4. So keep it in mind. We'll go this case, right? So shortest distance to node 5. What is the formula we can define? Shortest distance at the node I plus the distance from node I to reach node 5. So that is the things. So therefore, this is the shortest distance at the node I. So naturally, I is here 2, 3 and 4. For example, from 2 to node 5, the thing is what? At the node 2, the shortest distance in the stage 1 we observe it is 7. Right? Similarly, for 3, it is 8. Similarly, for 4, it is 5. Right? So now the corresponding distance, that is from node 2 to node 5, the distance is nothing but 12. So you can see the network, right? So that is from 2 to 5, the distance is 12. So similarly, you can go for the remaining thing also. So that is the things. For from node 3 to node 5, the distance is 8. From again 4 to 5, it is 7. So adding these values, we will get 19, 16, 20, 12, sorry, respectively. So among these, naturally the question is what? I have to choose the minimum distance. So therefore, the minimum distance is what here? 12. So how do you get that 12? I'll start with 1. Then I'll come back to the node 4. Then from node 4 to node 5. So if you want to reach the node 5 from 1, so the shortest route is what? 1 to 4, 4 to 5. Right? Not the other things. So similarly, one more node is there, that is node 6. Right? The same method we can analyze it here is also. So to reach node 6, there is only 2 possible. You can move from 3 to 6 or 4 to 6, not from 2. Therefore, here I omit the 2. So same things, the shortest distance at the node 3 plus the distance from 3 to node 6. That is the things 8 plus 9. Similarly, at the node 4, the distance from node 4 to node 6, it is 30. Right? So analyzing this one, among these two, 17 and 18, the 17 is the minimum. So what is the conclusion? That is from 1 to 6 if you want to move through the node 3 is the shortest distance, right? Node 3 is the shortest distance. Now again, these two conclusion, we can move for the next stage. Now the next one is what? The final stage. We have to reach from 5 or 6 to 7, right? Node 7. So therefore, the shortest node at 5, we already observed it is 12, and for node 6, it is 17. We already observed, right? So the next stage is we have to go for reach the node 7. So as usual, I have to talk, right? So to reach 7, what are all the possible things? I have to take from either 5 or 6 to reach 7. So from 5, the shortest distance is 12, and from 5 to 7, the distance is 9. So adding 12 plus 9, it is 21. So similarly for node 7, at 6 to 7, how do you reach? So at the 6, the distance is 17, and from 6 to 7, the distance is 6, right? So concluding these two, 21 and 23, we got it. So the minimum distance is 21, that is from node 5. So what I have to do? I have to come from 5 is the shortest distance. So if you go for 5, then the corresponding thing is nothing but 4, right? And from 4 it is 1. So therefore concluding, so for 7, 5 is the shortest distance here we are observed, and previous stage we observe the shortest distance to reach your 5 is 4, and for 4 from 1 it is net. So therefore the shortest distance, if you calculate, I have to go this is the way: 1 to 4, and 4 to 5, and 4 to 7. So here 1 to 4, 4 to 5, then 5 to 7. So this is the shortest distance, right? So and the corresponding route also we put it 1, 4, 5, 7. So that is the conclusion here. So we reach from 1 to 7 with 21 miles. So that is the things here, right? So I hope you can understood this example. Now going for the next things, maybe we can put this one in the standard form, right? So in previous example, we will put it in the word format only, the shortest distance at xi. So that one here you will put it in the mathematical sense, the distance from xi minus 1 to xi plus the distance assigned at the particular node, that one here fi minus 1 of xi minus 1. So that is nothing but taking these two, summing up, and take the minimum, that is we assume it as a fi of xi. So mathematically we observe. The next one is the principle of optimality. So what is the application here we are observed in this example? So one can take the in decision in a future. So based on the previous stage, right? So if you want to move for the next stage, I have to take a decision and from the current stage based on the previous stage. So that is nothing but talking about the principle of optimality, right? So now let's take one example based on the previous, the continuity. So instead of giving the network sense, they give it in the notation sense here. So here obtain the shortest route and its distance to the following routes using DP. So here what is this meaning? Reaching the node from 1 to 2, 5 kilometer. Again from 1 to 3 it is 9 kilometer. 1 to 4 it is 8 kilometer. Similarly 2 to 5, 10 kilometer. 2 to 6, 17 kilometer. Like that it is put it in the notation sense. So this easily one can draw by the network sense, right? So observe here. So for example 5 to 7 it is 8 miles, right? So 5 to 7 it is 8 miles. So you can put it in any way, but it should be put it in a little bit stylish format, right? So the network should be put it little bit stylish format, right? Acceptable sense. So don't put very confusion sense, right? So network should be very clear. So based on the observation, we observe this network. So based on this network as usual, like a previous example, we can split this one into stage one. That is stage one is consists of 1, 2, 3, 4, right? So this is stage one. And for stage 2, 2, 3, 4, 5, 6, right? And stage 3, 5, 6, and 7. So like a previous example, so we'll move for stage 1. So at from 1 to node 5, it is clearly 5. That is nothing but simply at the distance. From 1 to 3, it is the distance 9. 1 to 4, it is 8. So that is the things here also. The next one is what? I have to reach to 5 and 6. Naturally from 2, 3 and 4 are the possible. Similarly, to reach 6, naturally we can reach from 2, 3, 4. So in previous example, this option is cut for reaching from 2 for the node 6, right? But here it is allowed in this example. So the same things repetition as in the early example we have discussed, right? So for reach the node 5, so from node 2 it is 5 the distance, and from 2 to 5 the distance is 10, add it 15. Similarly for 3 the distance shortest is 9, and from 3 to 5 it is 4, that is 13. Similarly here the case for 4 it is 8, and from 4 to the node 5 it is 9, so it is 17. So among these the minimum is 30, that is through node 3 is the shortest distance. So similarly you can conclude for node 6 also, right? So based on these two observation, now move for the next stage, that is for reach the node 7, that is from 5 to 6, right? So for 5 the shortest distance we observe it is 13, and for node 5, right? So it is 17. So that is the things here we'll put it. So 13 plus, I think here a little bit, yeah, correct only. So 13 plus 8, right? So that is to reach the 7 from 5, the shortest distance is 30, right? So here the shortest distance at the node 6 is 70, right? So therefore that is the thing. So from 5 to 7 the distance is 8, from 6 to 7 is 9. So adding these values we will get 21 and 26 respectively. So the shortest is distance is 21. So therefore what is the conclusion? That is from 7 you can reach shortly from the node 5 only, right? Not from 6, right? So comparing these two, right? So comparing the previous things, so shortly we can reach from 5 only, not from 6, right? So to reach 5 the shortest is 3, right? Not 2 or 4. So again from 3 naturally you can go for the starting point. So the conclusion is what? That is the shortest distance to reach node 7 is nothing but 26. Sorry, this is I put it wrongly. This is not 26, 21 miles. This is 21 and not 26. This is 21. So please correct it. So the shortest route is 1, 3, 5, and 7. So this is the another example. Now the natural question is it possible instead of going from a forward motion, that is from node 1 to node 7 reaching in the previous example, think it about the other sense, that is starting from backward motion, backward recursion, right? That is starting from node 7, then I have to reach to the node 1, right? So this is also the same similar procedure with slight modification. There also you get the naturally you have to get the same shortest route and same shortest distance, right? So if you are going for the shortest case, either you are going from, for example, Chidambaram to Chennai or Chennai to Chidambaram, whatever things you will have to take the only the shortest distance, right? So if you go for the backward operation also, you will get the same answer, same route. So that is the next one, the backward accretion. So backward accretion is what? It is nothing but computation. Proceed from nth stage to so on, move to the stage 1. So here is an example. So it's based on the previous example itself. So concluding the observation, the function can be rewrite like this. Just from the previous mathematical form, I just replace the values, right? So instead of that, in previous example, it is xi minus 1 to xi, right? So here it is xi to xi plus, right? That is, I'm going like this. That is backward regression. Similarly, here fi plus 1 of xi plus 1. So that is the slight modification. So from example 1, we start with the node 7. So that one I take it by just notation as x4, that is 7, right? So naturally f4 of x4 is 0. There is no distance. That is my starting point. So now move from stage 3, then stage 2, then stage 1. So stage 3, I'll start with node 7. Then the node 7 is connected with 5 or 6, right? So I think maybe remember this network, right? So once again, I just recall that example. So this is the example. So from 7 to, you are moving backward, either 5 or 6. Again from 5, there are 3 possible. Either you can go for 2 or you can go for 3. Again for 6, either you can go for 3 or you can go for 4. Right? So similarly for 2, 3, 4 also. So this is the way you are moving the backward operation. So let's come back here. Yeah. So this is the thing. So I'll start with taking x4 as 7 and moving backward. So naturally x3 is either 5 or 6. So that is the things here. I'll put x3, 5 or 6. So according to the mathematical formula, so put I equal to 3 here. So that is f3 of x3. Right? That is stage 3 is the meaning. What is this? This is nothing but the distance from x3 to x4 plus f of x, right? So here we take x4 as 7. Now apply this formula here, moving from x3 to x4. So what is the answer? It is nothing but 9 for considering x3 as a 5, right? So similarly, f of x4 we already observed it is a 0. That is the initial point, that is 0. So similarly, taking x3 as a 6, then f3 of 6, right? f3 of 6 is nothing but 6 plus 0, right? Now adding these values, that is the things here I'll put it. f3 of 5 is 9 and f3 of 6 is 6. Here I'll put it. Now among these two, which is the optimality, which node gives the optimality? If you think it, so the only possible is nothing but sum. That is the previous one. Among the previous node, which is giving the optimal. So only one node, therefore naturally this is 7 only, right? So x4 asterisk is 7. If there is two things are there, then we can make an option. So here only one node is there, therefore there is no any option. Therefore simply we'll put the previous node, that is the optimality node, as sum. Now move for the next stage by taking from 5 and 6, move backward to 2, 3, 4. So for 5, we have to go from 2 and 4. For 6, again like from the previous network, let's go here. Right, so which is the next node connecting 2, 3, 4. That's why I'll take x2 as 2, 3, 4. And we have to move for the next stage 2, that is f2 of x2, put I equal to 2. So this is d of xi comma xi plus 1, right? So I put I equal to 2, therefore 2 plus 1. So here f3 of x3. So if I take the present node x3 as a 5, then what is the things? So here I have to put x3 equal to 5, x2 as a 2 if you consider this case, then 2 to 5. The distance in the previous stage we observed is a 12, right? And f3 of x3, that is from the previous table, we observed it is a 9. So therefore we'll put it simply, these are all 9s, right? So similarly, if I consider x2 as a 3 and x3 as a 5, then 3 to 5 it is 9, 8 plus f3 of x3 is 9. So like that you can put it all those things. Now if you go for thinking about this case, if I consider x3 equal to 6 and my x2 is 2, there is no a route to reach from 2 to 6. You go through the network, there you can observe it. There is no route, right? Therefore, it does not exist, right? Because the reason is what? There is no a route to reach from the node 2 to 6, right? So therefore, that is should not be considered. That's why I'll put it here. There is no path from 6 to 2, right? So therefore, we have to omit this case. Now think it about the next one. If I consider x2 equal to 3 and x3 equal to 6, then from 3 to node 6, there is a path, right? So their distance is 9 and corresponding f3 of x, that f3 of x3, that is x3 is 6. If I take f3 of 6, their value from the previous table, it is a 6. So adding this 50. So similarly here from 4 to node 6, it is 13 is the distance, and f3 of 6 is nothing but 6, that is here you put it, right? Now concluding this the case here. So among these two, which is the optimality, right? We have to, optimality means here talking about the minimum distance, shortest distance. Therefore here only one option, therefore I'll put 21. Here think it about here between 17 and 15, the shortest is 15. So therefore I'll put it here 15. 16 and 19, I'll put it here, the shortest is 60. So here I'll put it, right? Now which one node gives the shortest distance? For this 21, that is x3 equal to 5 is gives the 21, and for 15 the node 6 gives the shortest distance. That's why I'll put it here. The x3 has to take as a 6, not a, the other things 5, right? So here in this case the 16 gives by the node 5, therefore we put 5. So this is the optimality node. Now the final things, I have to move for stage 1 from the case 1. From node 1, I can take these are all the routes 1 to 2, 1 to 3 and 1 to 4. Right? The same step I have to take x1 equal to 1. Now according to the formula, put I equal to 1, f1 of x1 is equal to d of x1, x2 plus f2 of x2. So you take what are all the options for going back from 2 to 1 and 3 to 1 and 4 to 1. So again at the node 2 from the previous table we observe it is nothing but here 21, right? So that is at the stage at the node 2. So that is the things here. Put it f2 of x2 is 21, and from reaching from node 1 to node 2 the distance is 7. So that is the things here. So similarly from node 1 to node 3 the distance is 8, and for at the node 3 their corresponding f value from the previous table we observe it is 23, right? So here that is the previous table, right? 15, sir, 15. So 8 plus 15 it is 20. So similarly the same things for reaching from 1 to 4 the distance is 5, and at the 4 the shortest distance from the previous table we observe it is a 16 here. So that is here we will put it. So simplifying all this value, right? So 28, 23, 21, that is we are moving backward from 1 to 2 it is 28, from 1 to 3 it is 23, from 4 to 1 it is 23, right? Now among these you can choose the minimum. Among these you have to choose the minimum. So I think here I'll wrongly write it. It is not a 23, so it is 21. So please correct it. So this is 21. So among these three, the 21 is the smallest, right? The smallest value, that is the shortest distance. So therefore 21. So this 21 yields by the node 4, right? So therefore the optimal node is 4. Now we can conclude all those things. That is, we are starting from 7, the very shortest distance, the previous node we can reach. Thinking about 5 and 6, 5 is the giving the shortest distance. Therefore 5. Again from 5 to 4, that is this one. From 4 to 1. So this is the shortest route. The same things we can get it from the forward recursive motion in the first example as we discussed, and their corresponding distance is also 21 miles. That is also same things, right? So the answer, you will get the both the things, both forward and backward recursive, you will get the same solution. There is no change. So I think it's a very easiest example. Now, little bit uh, a small additional things we have to observe from this backward. Let us consider one more example. Think it about this example. So here, little bit complicated situation, because you think it about this nodes 2, 3, and 7. So in this stage, how do you conclude to split the stages? So it is little bit chaos in these stages. So what I have to do is I have to make the duplication. That is, I consider the duplication of 2 as something 2 prime, and 3 as a 3 prime, and 4 as a 4 prime. Only in this case, because so in between there is a distance is traveling path is there, right? Not here, right? So therefore, what is the things? I have to just make the duplication. Later I can settle it. So in that way, I have to talk the stages. So think it about here. So think it about this case. So these two case. So I split this 2, 3, 4 into 2 prime, 3 prime, 4 prime. Right? There is no changes for the remaining nodes. Now from 2 to 2 prime, because it is a duplication, there is no path. Therefore, I put 2 to 2 prime. There is no distance, because both are same things, only the notation wise. Therefore, I'll put the distance as 0. And similarly, from 2 to 3 prime. So that is 2 to 3 is 6. That is, here I'll put it as a 3 prime, right? Because I want to make it into stages. So therefore 2 to 3 we reach with 6 miles. So that is nothing but 2 to 3 prime, that is 6. So here I am no need to put the path here. So this 2 to 3 can be put it like this, 2 to 3 prime, right? So it is same. So similarly for taking the other cases also, that is reaching from 3 to 4. So sorry, 4 to 3, 4 to 3. So that one I have not put it here, but I can put it in other way. That is 4 to the duplication of this one, that is 3 prime. So 4 to 3 prime, I'll put 7. And similarly, there is no path, no need to assign for the duplication. Therefore, 3 to 3 prime, it is take it as a 0. This is for just like duplication sense. Similarly, 4 to 4 prime, there is no path. Therefore, I'll put it. Now, there is no any cross edges, right? There is no any cross. So now the thing is what, we can easily split it into various stages. So stage 1 concluding the node 1, and stage 2, 2, 3, 4, and for stage 3, 2 prime, 3 prime, 4 prime, and 5, 6 are stage 4, and finally the end node. Now as usual we can go by the backward recursive concept formula, so you can proceed easily, right? So all those things are just easy things. Maybe here one things I have to notice that I want to say. So think it about this case, for the both case, that is reaching 5 from 2 prime, and for reaching 6 from 2 prime, both the things are, you are getting the same distance, 16. So in that sense, what I have to do, I have to consider the both the things. That is, to reach 2 prime to 5 and 2 prime to 6 are having same distance. Therefore, the optimality nodes are both 5 and 6, right? So laterally we can conclude that case. So like that, we can think it about here also, that is 13 and 13, right? That is, to reach from 4 to 3 prime, it is 13. From 4 to 4 prime, it is, you will get 13, right? So both the things here, we have to take it as a optimality. Now I think it is very easy to observe the case, right? So you just go through it. So final thing is, the answer is from 1 to, that is 7 to 5, and 5 to 3 prime, and 3 prime to 2, and 2 to 1. But 3 prime, I already told it is just duplication of 3, therefore I simply replaced by 3, and corresponding miles are 70. That is the shortest distance. So I'll stop here at present moment. One of the small introduction will start with the dynamic programming problem. So any doubt for today's lecture, maybe you can contact me to make any clarification. So if possible, we can meet at the college. So I hope so. You're all enjoy my